Warning, something is deleting our galaxy. We're moving 600 kilometers every second toward an invisible wall. Galaxies around us slant the same way, like iron filings around a magnet we can't see. The map bends, then it tears. Past the Milky Way's glare, something heavy drags the night and the sky refuses to show its hand. Radio whispers hint at mass. X-rays flicker from hot gas. But the center stays dark. If we're in a drain, what's at the bottom? And what happens when the drain meets an expanding ocean? Tonight, I follow the current to a boundary that feels like physics is being quietly uninstalled. And I'm asking if the thing ahead is pulling us, or if something behind is pushing us out. The pull you can feel but can't see. This starts with a bruise on the oldest light. The cosmic microwave background is supposed to be smooth, a baby picture of the universe that looks the same in every direction, unless you're moving. When astronomers mapped that glow with balloons and satellites, a dipole popped out, one side warmer, the other cooler. Not because space was lopsided, but because we were. Our entire neighborhood was sliding through the background, and the background called us on it. And here's the part that hooked me. The arrow didn't point to something we could see. 600 kilometers per second. It's a number that feels reckless, like finding out your house has been slowly drifting downstream your whole life. Teams went back to their instruments, checked calibrations, blamed the foreground. Maybe our own galaxy's dust was faking the tilt. Maybe the motion was just the sun's orbital twitch. They peeled away local speeds, Earth around the sun around the Milky Way through the local group. The residue refused to vanish. The vector held. It pointed straight into a crowded swath of constellations, and right through the Milky Way's brightest stars. If there was a culprit, it was hiding where we could barely look. Now here's where the stakes land. Peculiar velocity is the part of your motion that isn't just the universe stretching. Hubble expansion is the tide that lifts all boats. Peculiar velocity is the sideways current that decides where you actually end up. If you get this wrong, your whole distance ladder wobbles. Redshift becomes a faulty speedometer. For years, reputations hung on which corrections to trust. People signed their names to numbers that could make their careers or stamp them as careless. Meanwhile, the sky told a consistent story. The dipole said this way. Independent catalogs, Tully-Fisher for spiral galaxies, surface brightness fluctuations for ellipticals, Type Ia supernova standard candles, each took a crack at the flow. The details disagreed, the scatter was real, but the arrows lined up more often than they didn't. Bulk flows emerged, not as perfect lines but as a chorus that leaned. Clusters that should have been happily riding the Hubble tide showed infall patterns, like leaves curling toward a storm drain we couldn't see. Get this? Astronomers literally bet coffee, pride, and months of weekends on tiny corrections. One team tore down and rebuilt a receiver because a Coke's run seemed too warm by a fraction. Another rewrote the pipeline to chase a systematic that turned out to be the night janitor switching lights the same time every Thursday. The motion didn't care. Every clean data set still pointed through a patch of sky smeared by our own galaxy's dust, where stars stack so thick they hide nearly everything behind them. That place has a name that sounds like a dare, the zone of avoidance. It's not empty, it's just blindfolded. Visible light gets shredded by dust, scattered by gas, drowned by the Milky Way's crowded lanes. If the pull was real, whatever sat behind that blindfold was heavy enough to bend the paths of galaxies over hundreds of millions of light years. Heavy enough to leave fingerprints on the microwave background. Heavy enough to make us feel it here. So what actually happened in the measurements? Start with the dipole. The warmer lobe aligns approximately with the direction our local flow leans toward, somewhere in the constellations Centaurus and Norma, low on the sky for many observatories, right in the glare. Subtract local motions and the residual persists. Survey by survey, the same gravitational hint pops up, a concentration that doesn't show cleanly in optical light, but does in radio hydrogen maps and X-ray flashes from hot cluster gas. Early on, people started calling it the Great Attractor, which sounded like a monster in the dark. The nickname stuck, even as the picture got more complicated. and the monster revealed itself as a crowded junction rather than a single beast. Impact-wise, this was a perspective switch. We weren't stationary passengers. We were in a current we didn't choose, and currents imply landscapes, valleys that pull, hills that push. The Great Attractor was less a dot on a chart and more a basin in a terrain we didn't yet have the resolution to draw. It mattered for everything from how we estimate galaxy masses to how we reconstruct the matter web around us. If your frame is drifting, your yardsticks, your clocks, your sense of at rest all shift under your feet. There was a human moment in all this that still feels close. A graduate student, wired on vending machine coffee, covered a whiteboard with arrows from a brand new peculiar velocity catalog. The arrows wouldn't sit still. They curved, they disagreed, but one stubborn line cut straight through the blind spot. The room got quiet, not because anyone had proven the mass on the other side, but because everyone felt the gravity of not knowing. The plan became simple. Stop pretending the splash was the story. Find the river. But every arrow pointed through a patch of sky we couldn't see at all. That wasn't a poetic problem. It was a practical one. If the Milky Way is your city's light pollution, the zone of avoidance is the highway glare right in your windshield. You shift wavelengths, chase the signal in infrared where dust hurts less, in radio where neutral hydrogen sings at 21 centimeters, in X-rays where hot cluster gas shines. You stitch partial structures across the plane like a torn map. The pull was real, the source was hidden, and the only way forward was to change how we looked and ask whether this Great Attractor was the destination or just the first signpost. The zone of avoidance, a built-in blindfold. To chase the river, we had to look straight through the Milky Way's worst glare. The zone of avoidance isn't a secret door. It's a smear of dust, stars, and gas that eats visible light. Billions of suns crowd the plane. Their glare washes out faint galaxies behind them. Dust grains the size of smoke scatter blue light, redden what survives, and turn the background into static. If there's a mass concentration pulling on us from that direction, it's hiding under our own front porch. That's the first mystery. The sky blocks the very lane our motion demands we follow. So astronomers changed the rules of seeing. You slide to infrared, where dust is less cruel. Suddenly, ghostly smears appear, galaxies peeking through gaps in the fog. Surveys like IRAS mapped warm dust and flagged hidden structures. Later near-infrared catalogs traced stellar bulges that had been invisible in optical light. Then you move to radio. At 21 centimeters, neutral hydrogen cuts right through the Milky Way's dust. HI surveys started painting arcs of galaxies behind the plane, their Doppler shifts giving distances, their distribution hinting at something bigger than a cluster. X-rays lit up the hottest gas, cluster atmospheres glowing where thousands of galaxies sit inside shared halos. Piece by piece, the torn map started to stitch. It didn't stitch cleanly. Extinction varies block by block. Some regions eat almost all visible light, others just bruise it. If you undercorrect for extinction, you miss galaxies and think the region is emptier than it is. Overcorrect, and you inflate counts, inventing structure where there's noise. Early claims of a Great Attractor as a single, monstrous overdensity grabbed headlines, but the data were messy. Some teams saw a wall of galaxies. Others saw hints of multiple clusters connected by filaments. The word attractor stuck because the flow pointed that way, not because anyone had a crisp picture of the beast. Here's the stakes check. Our entire motion rests on how we see through this blindfold. If the zone of avoidance is misread, the flow models skew. Peculiar velocities fail to converge. Distance ladders bend. Whole reconstructions of the local universe twist to fit a phantom. Careers rode on getting it right. A catalog missing 10% of galaxies in that strip shifts the inferred gravitational field like shaving a ridge off a watershed map. Meanwhile, the cosmic microwave background dipole didn't care about our confusion. It kept pointing. Action-wise, the hunt got specific. The Centaurus and Norma directions became ground zero. Radio telescopes combed the plane for hydrogen signals with velocities clustering around the same range. X-ray satellites like ROSAT and later missions caught hot plasma halos around hidden clusters. Norma, Able 3627, popped out as a heavyweight, not the entire answer, but a downtown in a broader city. Optical spectroscopy, when possible through low extinction windows, tied redshifts to structures hinted by radio and X-ray. The emerging picture, not a single monster, but a crowded region where multiple filaments and clusters converge, consistent with the Great Attractor, as a dynamical basin rather than a single body. The impact landed fast. Once you account for these hidden structures, the flow lines make more sense. Galaxies upstream show infall patterns consistent with a basin in that direction. Reconstruction methods, Wiener filtering, density-to-velocity inversions, use these incomplete cross-checked maps to turn galaxy positions and motions into a smooth gravitational landscape. The zone of avoidance remains patchy, but the bass note is clear. There's serious mass there, enough to tilt Laniakea's floor. The monster morphs into a terrain feature, a saddle near the plain with a deepening valley leaning beyond. And the complications didn't stop. Dust maps themselves had to be recalibrated. Foregrounds in microwave surveys, synchrotron free emission, overlap the same sky we're trying to see through. Malmquist bias sneaks in. Brighter objects are overrepresented, distances skew, and flows look faster or slower than they are. Teams fought these with better priors, redundancy across methods, and a lot of humility. You don't get to pretend the blindfold isn't there. You learn to see with it on. Human moment. A small group huddled in a control room while a 21-centimeter spectrum crawled across a screen. A tiny bump rose out of the noise. One galaxy, then another, then a dozen over the night. Each was a pinhole through the plane. Someone drew a quick sketch on a napkin, a chain running almost parallel to the Milky Way's spine, right where the arrows had been pointing for years. It wasn't dramatic on the page. It was devastating in meaning. The chain linked to known clusters north of the plane and hinted at continuity south of it. The torn map had a thread. Meanwhile, something else was happening downstream. As the blindfold thinned, evidence grew that the flow didn't stop at this hidden city. The alignments leaned farther, as if the valley's slope kept dropping beyond our stitched chart. That would matter later. For now, conquering the zone of avoidance turned the dark magnet into a crossroads, Norma and Centaurus as anchors in a larger convergence that our maps would later name Laniakea. The takeaway is simple and hard-earned. The pull we feel has a face, but it's a composite. Dust hid parts of it. Radio and X-rays gave us back pieces. The Great Attractor isn't a single object waiting to be photographed. It's a dense junction in a web. And once we saw it that way, the question changed from what is the dot to where does the river this junction feeds actually go? Cosmic rivers, from random dots to flows. To understand the pull, we had to stop staring at splashes and start tracing the river. Galaxies aren't pins on corkboard. They move. They slide along scaffolds of dark matter like water seeking low ground. If you only map positions, the sky looks like random freckles. Add motion, peculiar velocities, and the freckles turn to streamlines. You see direction. You see convergence. You see the landscape that gravity carved long before we arrived. And once I traced those streams, a larger pattern snapped into focus. Our arrows share a fate. Here's the stakes check. If galaxies flow, then where matters less than where to. Plotting points tells you what the universe looked like when the light left. Plotting flows tells you what the gravitational field is doing now. For people betting reputations on the current's direction, that difference is everything. A misplaced flow line means a misplaced mass, a mountain where there's a valley where there's a ridge. And that misread cascades into wrong distances, wrong masses, wrong stories about how structure grew. Action started with raw catalogs, distance indicators, Tully-Fisher for spirals, surface brightness fluctuations for ellipticals, type Ia supernovae where they were available, gave distances independent of redshift. Compare that distance to the redshift, subtract the Hubble expansion, and you get the sideways drift, the peculiar velocity. Do that for thousands of galaxies and clusters, and suddenly arrows sprout all over the map. They don't line up perfectly, they meander. But coherent bulk flows appear, regions where hundreds of galaxies share a leaning direction. On a whiteboard, this looks like chaos learning to whisper. Arrows splay and bend, yet there's a basin forming in the general direction of Centaurus and Norma. Clusters show infall patterns, front edges slightly blue-shifted, far edges slightly red-shifted, a telltale signature of material streaming toward a common low. It's not a single drain but a catchment area. The Great Attractor stops being a dot that gulps galaxies and starts being a dip in the terrain, a place where many filaments meet and guide traffic. To turn those noisy arrows into a landscape, you smooth with mathematics that respect the mess. Methods like Wiener filtering take the distances and velocities we trust, weigh them by their uncertainties, and reconstruct the underlying density and velocity fields that could have produced them. You start from a prior, usually a cosmology that matches the large-scale statistics of the universe, and let the data tug that prior into shape. The result is a flow field that you can trace like contour lines on a hiking map. Follow the arrows downhill, and you find basins of attraction. Follow them uphill, and you reach ridgelines where flows diverge. Meanwhile, something else was happening downstream. The reconstructed field didn't let the river end at the hidden junction. Flows didn't settle and stop. They curved past the zone of avoidance and kept leaning toward a deeper decline. That's the moment the story widened. The Great Attractor started to look like a median in a larger highway system. The real drop, the steeper grade, lay farther along toward the Shapley Concentration, which would later clarify the downstream weight. Impact-wise, this changed identity. We weren't orbiting a monster. We were residents inside a watershed, Laniakea, defined not by where matter is densest, but by where the velocity field says traffic ultimately goes. Our address became a dynamical statement. The Milky Way is one of tens of thousands of galaxies whose peculiar velocities converge toward the same sink. And that sink, when you trace the lines, isn't a pin. It's a region that includes the Norma cluster and flows that arc beyond it. The intuition flip is subtle but huge. Gravity only attracts, yet the map shows divergence from voids and convergence into basins. In a kinematic sense, voids behave like hills. Material slides away from them because there's less mass to hold it. Attractors act like valleys. The same law of gravity does both, but the network of over and under densities sculpts the field so that motion looks like water running off a ridge into a bowl. Once you see that, the push from emptier regions stops sounding like magic. It's the natural shape of the field. Human moment. A collaborator stared at a plot where flow lines bunched near a ridge, then forked. One fork bent toward the Virgo cluster, shepherding our very local traffic. The other fork curved through the blind spot toward the larger basin. He circled the fork in dry erase red and said, "This is where our neighborhood chooses." It was a small sentence with a heavy meaning. Our fate as part of one river and not another is baked into the terrain. Complications stayed honest. Distance indicators carry noise. Some catalogs oversample bright galaxies, letting Malmquist bias nudge flows outward. Undersampled voids make ridges look sharper than they are. Reconstructions depend on priors, choose different smoothing scales, and the edges of basins breathe. But across methods, across teams, the same melody kept coming back. Coherent bulk motion toward the Great Attractor region, then an unmistakable lean beyond. And that brings the tease that will matter next. If this basin is real and we're inside it, then downstream there should be a deeper well setting the overall slope. The arrows hinted at it. The reconstructions permitted it. The sense of a larger hand on the map grew. The Great Attractor, powerful as it felt, was starting to read like a waypoint. The river didn't end there. It flowed on, gathering more tributaries, answering to something heavier waiting farther out of sight. Laniakea, our cosmic watershed. Here, where the map stops being a dot hunt and turns into a living river. Researchers took those noisy arrows, the peculiar velocities that wouldn't line up, and asked a different question. If you follow each arrow downhill, where does it ultimately end? Not tomorrow, not next million years, but asymptotically, when the local jostling fades and only the broad slope matters. Trace enough of those paths, and a boundary appears not drawn by where galaxies sit, but by where they're headed. That boundary got a name: Laniakea, immense heaven. It's our basin of attraction, identified through flow reconstruction, with a local sink near the Norma Centaurus region. The stakes landed right away. We thought our home was the local group, a small neighborhood carved by the gravity between the Milky Way and Andromeda and a scattering of dwarfs. Then maybe we were part of the Virgo Supercluster, anchored by the Virgo cluster tugging nearby space. The flow map said both were too small to describe our true address. Our real home was a basin that gathers tens of thousands of galaxies into a shared fate. Belonging here isn't about membership in a club. It's about which way your velocity arrow ultimately points. Action-wise, the team built a dynamical atlas. Start with distances and peculiar velocities from multiple methods so no single yardstick dominates. Smooth with techniques that respect uncertainty, Wiener filtering, forward modeling, and reconstruct both the density field shaping space and the velocity field that rides over it. Then you do something simple and radical. You let virtual test particles flow along that field from their starting points. Where they converge, you declare a sink. Where they diverge, you declare a ridge. Connect the ridges and you sketch borders. Laniakea emerges as the catchment area of a major sink near the Norma and Centaurus region, the same direction where the arrows had been nagging us for years. The impact is an identity shift you can feel. The Milky Way stops being a lone ship with a few escorts and becomes one drop in a sweeping river. The Great Attractor, recast, is the sink of this basin, the place the lines head toward within the resolution of the map. But sink doesn't mean a single cluster you can circle with a pen. It's a dynamical feature spread across a region where flows decelerate and aim together. A gravitational low created by the collective mass of clusters, filaments, and the dark matter skeleton beneath them. Now remember, basins aren't just bowls, they have ridgelines. In this map, ridges are where neighboring rivers part ways. You can watch flow lines on one side peel toward Virgo, a modest shepherd guiding traffic in our near field, while lines on the other side trend past Virgo and bend toward the deeper south. Those ridges aren't physical walls. They're dynamical divides. A galaxy nudged across one by a merger or a long-term drift can end up in a different fate channel. But for most of the traffic, the lines hold. The watershed is real. Human moment, someone in the room said, let's name it like explorers. Laniakea stuck because it framed the scope without pretending to completion. It said, this is big, humbling, and navigable only by reading the stars. On release day, phones lit up. People didn't argue about whether the Virgo cluster exists. They argued about the boundary drawn by motion. That was the point. The map wasn't telling us where matter piles highest. It was telling us where history is dragging us. Complication, plenty. Flow reconstructions depend on priors. Distance errors smear streamlines. The zone of avoidance still bites, so parts of the basin's edge are sketched from indirect hints. Change the smoothing scale and the exact border wiggles. But across reasonable choices, the structure persists. You get a coherent catchment feeding a sink near Norma, a secondary guide near Virgo, and a shared lean that refuses to die when you swap catalogs. Here's the twist the arrows had been whispering since the last section. When you follow the flows inside Laniakea, many don't stop at the sink. They bend. Downstream, the grade steepens again. The velocity field keeps tilting toward a weight farther out. In hiking terms, the bowl pours into a deeper valley. In traffic terms, the city center funnels onto a freeway that heads to a bigger metropolis you haven't reached yet. The Great Attractor becomes a junction. The river doesn't end there. It leans toward the Shapley Concentration. Impact again, but downstream. This reframes risk and reach. If our basin is leaning toward a heavier weight, then today's convergence is part of tomorrow's migration. We can belong to Laniakea and still be passengers on a longer route that arcs past it. That tension matters when we talk about horizons and what expansion allows us to ever actually meet. It also matters for meaning. If your home is defined by motion, then your identity includes where you're going, not just where you stand. Microstory, late-night fluorescent buzz, a plot with streamlines overlaid on a skeletal web. A thin ribbon of flow peels off the Virgo-guided branch and threads the blind spot. Someone taps the screen. This line is us. Silence, then a laugh that sounds like plea and pride. That arrow doesn't know our calendars or languages. It only knows the slope. So what's the takeaway you carry? Laniakea is our watershed, drawn not by brightness but by destiny of motion. The Great Attractor is its local sink, the place our lines collect before they lean again. Virgo is a nearby traffic officer, not the final courthouse. And the boundary itself is alive, ridgelines where decision happens, where tiny nudges decide which future you flow into. Because downstream, something heavier was warping the entire the hidden weight downstream. While we were celebrating the map that finally gave Laniakea a shape, the arrows were already filing an appeal. They leaned past the sink. Beyond the hidden crossroads near Norma and Centaurus, the grade kept dropping. If the Great Attractor was the city center, the freeway out of town pointed to a skyline we hadn't really faced. Downstream sat a domain with its own gravity, louder and farther. The Shapley Concentration, an exceptionally rich supercluster complex whose mass explains much of our downstream lean. Here's the stakes check in plain terms. If the deeper slope lies beyond our basin, then our motion isn't just local housekeeping. It's regional weather. That matters for how we measure distances, how we calibrate supernovae, and how we tell the story of where we live. Get the deeper pull wrong, and you bias every yardstick tied to redshift. You misread how fast structures assemble. You assign blame to the Great Attractor for traffic it's only directing, not causing. In other words, you mistake a junction for a destination. Action moved quickly once the suspicion sharpened. Redshift surveys that looked past the zone of avoidance began to reveal an enormous overdensity farther along our velocity vector, hundreds of millions of light-years out. Catalogs of rich clusters, able catalogs and their refinements, flagged an unusual crowding of massive clusters packed into a swath of sky in the direction of the constellations of Centaurus and Horologium. X-ray observatories saw the telltale glow of hot intracluster gas, the plasma halos that make giants obvious even when their galaxies blur. Stacking these signals, a picture emerged: the Shapley Supercluster, a concentration so heavy it warps flow fields over vast scales. Meanwhile, the velocity reconstructions kept nudging the same way. Trace streamlines from our neighborhood through the Great Attractor region, and many bend toward Shapley like a river pulled by a deeper canyon downstream. Bulk flows that seemed to converge near Norma did not terminate there. They reoriented. Kinematic signatures, far-side redshifts and near-side blueshifts across cluster complexes, showed infall patterns feeding not just the local sink, but a larger basin slope beyond it. What started as a nickname, Great Attractor, got demoted to waystation by the math. Impact hit hard in the community. The reframing was simple: the Great Attractor channels, Shapley dominates. Mass estimates for Shapley carry big error bars, selection effects, incomplete sky coverage, messy cluster membership. But every method kept it big. Tens to hundreds of rich clusters nested in filaments, hot gas lighting the scaffolding, gravitational footprints stamped across flows we could measure from home. Once you fold Shapley into models, the amplitude and direction of our peculiar velocity look less mysterious. The deep valley explains the lean, especially when balanced against the opposite underdensity. Human moment. A senior astronomer put down a marker and said, half relief, half dread, "We've been blaming the wrong mountain." The room laughed quiet. Solving a mystery by finding a bigger one is classic astronomy. You spend years arguing over a local sink, then discover the basin slope owes rent to a heavier landlord farther out. Now not every arrow bows to Shapley. The local web is tangled. Virgo still shepherds near-field motion. Other concentrations, Hydra, Perseus Pisces, the South Pole Wall, tug on their neighborhoods. The cosmic web is a compromise of poles. But when you average over the noise and let the data speak with weights that match their uncertainties, a coherent story survives. The direction flagged by the cosmic microwave background dipole, the peculiar velocity catalogs, and the reconstructed velocity fields points past the Great Attractor toward Shapley. Complications keep us honest. Selection biases haunt redshift surveys. Brighter clusters get cataloged first, skewing perceived structure. The zone of avoidance still erases lines right where we love continuity. Distance indicators carry intrinsic scatter. Malmquist bias can inflate inferred flows in undersampled regions. And X-ray luminosity is a messy proxy for mass. Cluster physics, cool cores, mergers, jitter the relation. So mass estimates for Shapley arrive with caution labels. Yet the convergence of multiple, imperfect probes is exactly what gives confidence. Different messes, same conclusion. There's a subtle intuition flip hidden here. Calling something an attractor makes us think of a point that swallows. But Shapley, like the Great Attractor, is not a drain plug. It's a sprawling depression in the gravitational landscape, a complex of valleys nested inside a broader low. Flows don't drop into a singular place. They decelerate into regions where the field lines converge, then curve again if the larger scale slope keeps falling. That's what the reconstructions imply. Laniakea pours toward a local sink, then tips down a ramp that aims at the Shapley domain. Microstory. A researcher scrolling through a three-dimensional render of the density field paused, rotated the view, and watched a filament, ours, thread the blind spot, brush the Norma hub, then arc toward a knot of clusters glowing in X-ray overlays. There, she said, not triumphantly, but like naming a distant relative you've only seen in grainy photos. That's where the floor goes. Impact, personally, is an identity shift twice removed. First, we traded the local group for Laniakea. Now we accept that Laniakea itself leans towards Shapley's deeper stage. Belonging becomes layered. Local tides here, basin membership there, downstream allegiance to a heavier weight beyond. It is less a mailing address than a travel itinerary written in gravity. And yet one more perspective tug waits at the edge of the map. If Shapley sets the deeper slope, why does our motion fit even better when we include something else? A push opposite Shapley's pull. The flow looks symmetric only when we admit a second actor, not a mass but an emptiness. The next bend in the river isn't just about what's ahead. It's also about the hill behind, the Dipole Repeller. The Dipole Repeller, a push from the void. So if Shapley is the deeper valley ahead, why does the model still feel off unless we factor in something behind us? Here, S where the map flips intuition. Gravity only attracts, but motion through a lumpy universe creates patterns that act like pushes. In the reconstructed velocity field, there's a broad, underdense region roughly opposite Shapley that behaves like a hill. Streams flow away from it. In kinematic terms, it repels. People started calling it the Dipole Repeller, a kinematic repeller inferred from velocity field divergence, not a new kind of force. Stakes first. If our 600 km/s drift is shaped by both a pull toward mass and a push away from emptiness, then ignoring the void breaks the symmetry. Our distance measures skew. Our calibrations wobble. We misread the basin's boundaries and overcredit the Great Attractor for motion the void is helping to drive. The consequence isn't abstract. Every galaxy in our catalog sits in a field sculpted by both valleys and hills. Get either side wrong, and you misplace where the river should run. Action came from the same engine that revealed Laniakea, velocity reconstructions that translate noisy, peculiar velocities into smooth density and flow fields. When researchers inverted the flow to map out not just where mass collects, but where it's missing, a coherent underdensity bloomed opposite the pole. In that region, streamlines splay outward. Test particles seated inside are carried away along multiple filaments. It's not anti-gravity. It's gravity doing exactly what it should when there's less matter in one place than around it. Think of a gentle rise shedding rain. Meanwhile, something else was happening across town in the data. When the model included both Shapley's pull and the void's effective push, the predicted direction and amplitude of our peculiar velocity lined up better with the cosmic microwave background dipole. The residuals shrank, the fit improved, the "but they're still missing momentum" argument lost steam. In other words, the void mattered as much to our trajectory as the famous concentrations of clusters we love to put on posters. Impact hit in the way we talk about flows. The community started leaning into the Valley Hill language. Attractors are valleys where streamlines converge. Repellers are hills where they diverge. The math is still gravity. The narrative gets clearer. You can trace our arrow as a compromise between an escape from the underdensity and an approach toward the overdensity. The words push and pull here are metaphors for the shape of the field, not new forces, but they help you feel the current. Complications kept everyone cautious. Voids are hard to sample. By definition, there are fewer galaxies to trace. Selection effects bite harder in emptiness. A shallow survey might miss the few faint galaxies that define the boundary, making the whole look larger or deeper than it is. Reconstructions depend on smoothing scales, change the filter, and the apparent crest of the hill shifts. Distance errors propagate badly through inversions. Malmquist bias can make outflows look faster. And yet, across reasonable choices, a large underdensity in the opposite hemisphere kept reappearing, and the kinematic signature, divergence, persisted. Human moment. In a cramped office, a postdoc slid 2 plots across a desk. One had only attractors. The arrows leaned, but the fit to the microwave background wasn't pretty. The second plot added the void. The main streamlines sharpened, the angle tightened, the numbers breathed a little easier. "It's not a monster," she said, tapping the blank patch. "It's a missing." The room nodded, the kind you do when absence suddenly feels active. Here's the intuition flip that rescues sanity. We're trained to think force when we hear repeller, but the universe doesn't need new forces to make outflows from voids. With less matter to pull inward, surrounding regions dominate and motion peels away. Kinematically, that looks like a push. Dynamically, it's a lack of pull. Frame it as water again. A broad dome shed streams down its sides, even though no source is shoving uphill. The shape alone dictates the flow. Meanwhile, add a tease. When you include the dipole repeller, the basin edges of Laniakea make more sense. Ridges become cleaner where flows split between Virgo's shepherding and the longer arc toward Shapley. The local web stops looking arbitrary and starts looking like the natural compromise between fleeing a hill and sliding into a valley. And that clarity feeds straight into the next dilemma we can't avoid. The river we're following is flowing through a landscape that itself sits inside an expanding ocean, accelerated by dark energy. Impact, personally, is acceptance. Our motion isn't a single heroic arrow spearing a target. It's a negotiated path between emptiness and fullness. That's not just poetry. It's why the map feels stable once you balance both sides. Get this balance right, and the story of the Great Attractor and Shapley settles into place. A valley ahead, a hill behind, a current that makes sense of the bruise on the oldest light. Now the current had both banks, the valley ahead and the hill behind. The map isn't the territory, uncertainties and blind spots. Here S where humility earns its seat. We've drawn a river, named a watershed, pointed to a valley and a hill, but the map we're holding is stitched from partial glimpses, noisy yardsticks, and choices that leave fingerprints. The zone of avoidance still crosses our chart like duct tape. Selection effects lean our samples. Biases creep in when we only see the brightest or the nearest. The story holds, but the edges blur. Stakes first. If we misread the fog, we don't just get pretty borders wrong. We tilt the entire velocity field. Distances bend, masses shift, error bars hide overconfidence. A small skew in one catalog propagates like a rumor into reconstructions that dozens of papers build on. People hang careers on which priors they choose, which distances they trust, which smoothing scale calms the noise without flattening the truth. This isn't pedantry. It's whether our 600 km/s arrow actually means what we think it does. Action is a grind of cross-checks. Spiral galaxies offer Tully Fisher. Rotation speed ties to luminosity. giving distances that don't depend on redshift. Ellipticals give surface brightness fluctuations. The grain of starlight tightens with proximity. Type Ia supernovae, when we catch them, standardized like lighthouses with known wattage. Each method has its own weather. Tully-Fisher scatters when galaxies are face-on or dust-laden. Surface brightness fluctuations wobble with stellar populations. Supernova standardization depends on light curve fits and subtle host galaxy trends. None is a silver bullet. Together they form a jury. Meanwhile, measurement noise doesn't behave. Malmquist bias slips in. In any flux-limited survey, brighter objects overpopulate the sample. That drags average distances outward and can fake a flow if you don't correct carefully. Peculiar velocity catalogs overrepresent clusters with many spectroscopic redshifts and underrepresent lonely field galaxies, sharpening structures that might be shallower. The zone of avoidance still removes pinholes where we most need continuity. We rely on radio and X-ray where optical dies, but those bring their own selection quirks. X-ray luminosity is a jittery mass proxy. Mergers puff it up, cool cores dim it down. So reconstruction teams play both offense and defense. Offense: push deeper, fill holes, add distance indicators that don't share systematics. Defense: simulate the pipeline, inject fake skies, and see how well the machinery recovers known inputs. Methods like Wiener filtering help by assuming the universe's large-scale statistics, then letting data tug that prior into place. But priors are choices. Change the smoothing scale and a ridge soften. Tighten it and a basin bites deeper. The art is choosing scales that the data can actually support. Human moment. A collaboration sat around a table arguing over a single histogram, distance residuals from one catalog against another. The mean didn't matter, the tails did. One senior voice said, "We don't need this to be pretty, we need it to be honest." They widened the error bars, published the uglier truth, and watched their flow map breathe. Ridges less cocky, sinks broader, confidence intervals that actually matched reality. What nobody knew at the time, across different teams and different priors, was how consistent the melody would remain. Every catalog sang off-key in its own way, yet the chorus still leaned. Flow toward the Norma, Centaurus crossroads, a reorientation downstream toward Shapley, and divergence from an opposite underdensity. The map's boundaries wavered, but the current didn't flip. That's the kind of robustness you bet on, not perfection, but persistence across independent messes. Still, there's a price. Foregrounds in the microwave sky, synchrotron from electron, free from ionized gas, bleed into the same patches where we chase the dipole's direction. Dust maps used to correct extinction near the plane carry their own assumptions. Recalibrate them and your census of hidden galaxies jumps. Distance ladders depend on local calibrators, Cepheids, tip of the red giant branch, tied to metallicity and crowding. Shift one rung and the whole ladder lists. This is why velocity fields come with fat covariance matrices, and why cautious papers spend pages on systematics. Here's the impact that matters. Uncertainty doesn't erase the river, it thickens the fog around its banks. Our confidence lives in the interior, inside Laniakea's flows where multiple indicators agree and the zone of avoidance bites less. At the edges, near ridges, across the plain, far downstream, the story admits wiggle. Borders are provisional. Sinks are regions, not pins. And when we talk about the Dipole Repeller, we keep the word kinematic close, because voids are sparse and easy to overstate. Micro story. A grad student watches a map update after a reweighting of distances in a poorly sampled sector. A ridge shifts by a few megaparsecs. She exhales like she's been holding her breath for months. The arrow marking our path barely moves. So the road meanders, her advisor says. The destination holds. That's the takeaway. The map isn't the territory. It's a living guess that improves when we argue with it. We name what's stable, the direction of motion, the presence of a basin, the lean toward Shapley, the hill behind, and we hold the borders with an open hand. With the river charted as honestly as we can, one question lingers at the edge of every plot. What happens when this current meets the expanding sea it flows through? expansion versus attraction, a tug-of-war you can't win. While we've been tracing valleys and hills, the whole landscape has been stretching under our feet. That stretch, the Hubble flow, isn't a breeze you can lean against. It's the metric itself changing, space adding more space between distant markers. Gravity tries to gather, expansion keeps adding distance. The river we're in doesn't flow through still air. It runs through a rubber sheet that's being pulled at the edges. And since the late 1990s, we know that pull is accelerating. Here's the stakes check. Attraction can pull you toward a valley, but expansion sets a moving finish line. Past certain scales, the recessional speed from expansion outpaces any gravitational pursuit. That's not a speed limit law, it's geometry. Galaxies far enough away recede faster than light, not by breaking physics, but because the fabric between you stretches faster than light can close it. If the deeper slope of our basin, the Shapley domain, sits beyond the distance where expansion wins, then the current can point that way forever and never deliver us. Action-wise, think in zones. Nearby, inside a few tens of millions of light years, gravity rules. The local group is bound. The Milky Way and Andromeda are on a collision course that ignores cosmic expansion because their mutual gravity overwhelms it. Widen the view to the Virgo cluster scale, tens of millions to 100 million light years, and gravity still shapes orbits and infall. Widen further to supercluster scales, hundreds of millions of light years, and now attraction and expansion wrestle. At some radius from any attractor, the Hubble flow equals the local escape speed. Inside that turnaround region, matter can fall in. Outside it, recession drags faster than gravity can haul back. Meanwhile, dark energy tilts the odds. A few decades ago, late 1990s, Type Ia supernovae made it clear the expansion isn't just continuing, it's accelerating. That acceleration makes the turnaround radii smaller in the long run and pushes the universe toward isolation. Structures that are already bound will stay bound. Loose associations won't tighten. Filaments will thin. Voids will grow. The riverbeds we've mapped will become drier courses etched in a sheet that stretches faster every era. Now bring this back to our arrow. Follow the flow lines through Laniakea, through the Great Attractor sink, and they lean toward Shapley's basin. But the decisive question isn't only direction, it's reach. Is the Shapley domain's bound region big enough to catch us? Or do we sit outside its future handshake, condemned to forever approach without arrival? Current distance estimates place Shapley hundreds of millions of light years away. Its mass is vast, but so is the time. Many reconstructions suggest we're feeling its slope, without being destined to cross its effective horizon, consistent with dark energy shrinking turnaround radii over time. Impact hits as a quiet paradox. We can be pulled toward a shore that recedes faster than we can swim. The bruise on the microwave background, the arrows on our whiteboards, all point downstream, yet the downstream keeps moving. It's like paddling toward a dock in a river whose current strengthens with distance. Your heading is true. Your progress is real in your local water, but the dock drifts away faster than your strokes add up. Human moment. In a seminar room, someone asked, "So do we ever get there?" The speaker paused. "Define there." The room laughed, then went still. Because here's the nuance that matters. Getting there can mean different things. Kinematically, our velocity vector can align with Shapley's slope for a very long time. Dynamically, only matter inside Shapley's bound basin will eventually settle into its clusters. Observationally, future astronomers in our galaxy will see less and less of that downstream as acceleration redshifts its light beyond detectability. The arrow persists. The destination fades. Complications deepen the caution. Boundaries like turnaround surfaces aren't crisp on tangled terrain. Multi-body poles, time-varying mass assembly, and the coarse resolution of our reconstructions blur edges. Our peculiar velocity today isn't a promise written in stone. Local mergers, encounters with filaments, and tidal forces can nudge pathlines over gig-years. But dark energy sets the overall trend line. The universe's expansion will keep diluting the influence of faraway basins. What falls in now will keep falling. What sits outside the leash length will drift toward private skies. Here, where meaning tightens. The push-pull story that made our motion make sense turns into a lesson about limits. Gravity gives us a river. Expansion gives us shores that recede. Both are true. Both operate everywhere. Our identities as members of Laniakea, as travelers leaning toward Shapley, and as residents of a cosmos sprinting apart aren't contradictions. They're layers. On small scales, gravity wins. On intermediate scales, it negotiates. On the largest scales, it loses. Meanwhile, something else is quietly happening to the map itself. As acceleration stretches wavelengths, the distant web slides out of our observational reach. Photons from far downstream structures redshift into bands our detectors can't catch. The cartography of flows we're building today will be impossible to rebuild in a few tens of billions of years. The river won't stop. The lights that reveal its banks will. Microstory. An astronomer steps outside after a late run of code, looks up and thinks about Andromeda on its way, the Virgo cluster standing guard, the Great Attractor as a junction, Shapley as the downhill pull, and the acceleration humming beneath it all. She knows our arrow won't idle. She also knows the ocean's edge is moving. So what do we carry? A clear-eyed acceptance that we inhabit a tug-of-war you can't win at the largest scales. We can measure the current, map the basin, feel the valley and the hill, and still face a horizon we'll never cross. If we can't reach the valley, then what exactly are we moving toward? If we can't reach the valley, then what exactly are we moving toward? Here's a lens, not a claim, that makes the map feel uncomfortably familiar. Think of our sky like a rendered world with limited bandwidth. Where the story's busy, the engine spends detail. Where nothing much happens, it saves compute. The zone of avoidance stops being just dust. It reads like a culling mask. The flows we trace look like an engine prioritizing motion paths over pretty textures. I'm not saying we live in code. I'm saying the way we're forced to see, through proxies, with adaptive detail, rhymes with how any finite system would allocate attention. Stakes first. This metaphor risks seduction. It fits too well. That's why we handle it with tongs. But notice how our evidence behaves when viewed through a rendering edge frame. We're starved exactly where throughput is worst, behind the Milky Way's glare. We recover information by swapping to cheaper channels, infrared, radio, X-ray, the way a graphics engine drops resolution in peripheral vision. Our reconstructions, by necessity, are level of detail maps. High fidelity near, smoothed far, aggressively compressed at the plane. If reality had to economize, it would triage like this. Action-wise, follow the cues. In a game world, the engine tracks what matters to gameplay, collision meshes, navigation graphs, physics triggers, then backfills eye candy. Our cosmos presents the same priority list. The velocity field comes through even when the image blurs. We can lose individual galaxies to dust and still recover the river because the kinematic nav mesh survives. Voids act like zones with minimal updates. Low contrast, low entropy, easy to compress. Attractors red like high-traffic hubs where computation spikes. Hot gas glowing in X-rays. Mergers lighting up shock fronts. Tangled multi-stream flows that demand finer resolution. Meanwhile, something else clicks into place. Our biggest blind is not random. The zone of avoidance sits right where the flow bottlenecks through Norma and Centaurus. If you were optimizing a render, you'd spend cycles on convergent dynamics, not on resolving every faint background galaxy threaded behind foreground glare. That's what we're forced to do observationally, route around expense with proxies. 21-centimeter lines pierce dust like a debug overlay. X-ray halos expose mass like bounding volumes. The picture becomes less photograph and more wireframe, and yet it's the wireframe that moves the story. Impact is a meaning shift. The reality loophole here isn't proof of code. It's the recognition that our map mirrors how any finite observer would allocate attention. Entropy flows downhill, structure forms where gradients are steep, and information theory says you shouldn't waste bits where nothing changes. The cosmos behaves as if it respects a budget. Render the basin where galaxies crash. Lossy compress the voids where time is quiet. The place we can't see cleanly also happens to be where the pathlines pinch most, exactly the sort of seam a renderer hides under a foreground layer. Let's get concrete about the parallels and the limits. Level of detail in graphics swaps a complex model for a simpler one with distance. Our surveys do this by force. We bend, we smooth, we accept coarser features as we reach out. Occlusion culling hides objects blocked by a nearer mesh. The Milky Way's dust is literal occlusion. Garbage collection reclaims memory from unused assets. Cosmology has an analog in how voids expand and thin, but the collector is gravity plus expansion, not a scheduler. These are analogies, not homologies. Physics doesn't need a server. It only needs gradients, conservation laws, and time. Human moment. A researcher stared at a velocity field colored by divergence and convergence, blue bowls, red domes, and said, "If this were a sim, you'd keep the integrator tight here and decimate triangles there." Everyone laughed because it was absurd and apt at once. The math forces the same triage, where streamlines fold caustics, multi-stream regions, small errors blow up. You refine. In quiescent voids, coarse works. What nobody knew at the time was how sticky this metaphor would be once it helped people keep the moving parts straight. Call the basins high-resolution zones. Call the voids compressed backgrounds. Call the zone of avoidance a mask. Then remind yourself out loud, this is a storytelling prosthetic. The universe doesn't owe us convenience. It only gives us laws that, when averaged, make busy places data-rich and empty places cheap. Complications stack up if you take the metaphor literally. There's no evidence of dropped frames or quantization noise in the cosmic microwave background beyond instrument limits. Large-scale statistics match predictions from simple initial conditions stretched by gravity, not from an adaptive measure gone wrong. And yet, the workflow we're forced into, prioritize flows over images, proxies over direct sight, dynamics over decor, keeps rhyming with rendering logic. That rhyme is useful. It keeps us from worshiping pretty pictures and pushes us toward the physics that actually sets fate. Great Attractor as junction, Laniakea as basin, Shapley as deeper valley, Dipole Repeller as kinematic hill. Meanwhile, one detail proves crucial for the next step. If the engine allocates fidelity where mass and motion concentrate, what happens to the parts of the map with nothing left to do? Our flows don't just converge, they also evacuate. Voids are not passive backdrops. They balloon as matter drains off their slopes. In computing, that's where the garbage collector wanders, freeing memory nobody's using. In our sky, it's where the hill grows as the valley deepens. And that's where the second loophole waits, how a universe tidies itself by moving what it no longer needs. Reality loophole II, cosmic garbage collection. If the rendering metaphor helped us see where the engine spends detail, this next lens asks how it reclaims it. The cosmos looks like it tidies itself by moving matter out of low-value regions and stacking it where the action is. That's not a new force. It's gravity plus expansion acting like a cleanup cycle. Voids thin, filaments shuttle, clusters hoard. From our seat in the river, it feels like maintenance. And the psychology lands. If we're cargo on that route, what exactly gets kept, and what gets quietly deleted as space accelerates? Stakes first. If the push from voids and the pull to wells are two sides of the same housekeeping, then our 600 km/s drift isn't destiny, it's throughput. Misread that, and we turn natural kinematics into omens. Get it right, and we can predict which zones keep their matter and which are headed for bankruptcy in the long run. This matters for how we model structure growth, for how we set expectations about the far future sky, and for how we place meaning on our motion. Action begins with the kinematics we already trust. Follow streamlines outward from an underdensity, they fan. Drop tracers in a void's interior, they accelerate away along multiple exits. That divergence is the kinematic signature of a repeller. Now follow streamlines into a cluster complex, they converge, slow, and pile. That convergence marks an attractor. Stitch these behaviors across the web and a cycle appears. Voids evacuate, filaments ferry, clusters accumulate. The field evolves as the hills grow taller and the valleys deepen, not by fiat, but because gravity moves matter down gradients while expansion stretches the lowlands fastest. Meanwhile, something else is happening beneath the language. Entropy climbs when structures form. Gas shocks in filaments, heats in cluster halos, and eventually radiates energy as it cools or feeds stars and black holes. These are high-entropy theaters. Voids, by contrast, are low-contrast, low-interaction zones, cheap in information. If you were managing a budget, you'd free memory there and focus cycles where gradients are steep. The universe doesn't choose, but physics funnels it the same way. That's the rhyme with garbage collection. Identify what's unused, move live objects together, free the slack. Get this concrete. Think of filaments as buses. Their roots trace the dark matter skeleton. Small halos dwarf galaxies, loose groups bored over billions of years. They ride inward, sometimes merging on the way, sometimes surviving to be stripped in a terminal depot. The depots are clusters, deep potential wells, Norma, Coma, Perseus, where hot plasma glows in X-rays and velocities spray in 3 dimensions as infall turns to orbit. Around the hub, tidal fields shear newcomers. Star formation quenches as gas is shock-heated and ram pressure stripped. The stop is not rest, it's processing. Human moment. A simulation team watched a time-lapse of a void inflate as a filament brightened and a cluster core thickened. Someone said softly, "The bus routes got rerouted." Another voice, "No, ridership just increased." Same picture, 2 stories. Matter left quiet neighborhoods for a downtown that never closes. Impact lands in the meanings we assign. Our motion looks less like a pilgrimage to a sacred mountain and more like supply chain logistics. Gravity collects. Expansion incentivizes emptiness. The Dipole Repeller is a hill shedding traffic. Shapley is a depot swallowing throughput. If that offends romance, it sharpens prediction. Where will the next mergers occur? Along active routes. Which regions will starve? Those far from trunks, high on hills. Why do voids grow? Because every outbound path is downhill, and expansion stretches the plateau in between. Complications keep us careful. Clusters do not hoard forever. Feedback from active galactic nuclei heats gas and can stall cooling. Mergers slosh cores and scramble X-ray proxies. Filaments can be severed by environment changes. Group preprocessing alters what arrives at the depot. And the collector here is not an agent. It's emergent behavior from initial conditions seeded in the early universe and evolved by gravity in an expanding background. The metaphor helps, but physics holds the pen. Meanwhile, the cleanup cycle interacts with dark energy. Acceleration doesn't just pull distant docks away, it also freezes long routes. Buses still run locally, but far-travel commuters miss connections as the timetable stretches. Bound structures continue processing arrivals within their turnaround radii. Beyond that leash flows asymptote without capture. In code words, the collector compacts memory within islands and abandons fragmentation across the sea. Here's where micro-stories make it personal. A galaxy drifting inside a filament feels a steady headwind of hot gas rising as it approaches a cluster. Its spiral arms fray. Its star formation flickers, then dims. It doesn't know the word Laniakea. It only knows drag and tides. Another galaxy deep in a void watches its nearest neighbors recede. Encounters become rare. Its gas goes unshocked for eons. It ages into red quiet, untouched. 2 lives, same laws, different legs of the cleanup. One detail proves crucial later. Garbage collection gets efficient when live objects are compacted. The universe does this brutally well. By the far future, more mass will live in massive halos while interstitial regions stretch to near vacuum. Information density centralizes. Observability decentralizes. That dual trend creates our Loophole 3, the edge where local rules still hold but the large-scale map changes character under coarse graining. The takeaway is simple without being small. The push from voids and the pull to wells are the visible hands of a cleanup that requires no overseer. Our arrow is part of housekeeping. We are cargo on a route drawn by gradients, riding a schedule set by expansion. That doesn't drain the wonder. It relocates it. From the destination we may never reach to the machinery carrying us there. Boundaries where laws get weird. We've been leaning on gravity, flows, valleys, and hills, but there's a scale where the rules we trust start acting sideways. Not broken, just reframed. At supercluster scales, the neat intuition we built from planets and orbits snaps. The velocity field folds on itself. Densities stop adding linearly. And the one path to the sink, picture fractures into many overlapping streams that share the same space without sharing the same motion. This is where Laniakea's borders breathe, and where the Dipole Repeller's crest depends on how you smooth. Here's the stakes check. If you misread this edge, you invent new physics where you only needed new language. You chase ghosts, mysterious repulsions, exotic drags when the culprit is coarse graining. The laws haven't changed. The way we describe them has. And if we don't adapt, our map lies. Caustics masquerade as walls. Multi-stream regions look like contradictions. We start drawing decisions where nature drew folds. Action starts with nonlinearity. In the early universe, density contrasts were tiny. Linear theory worked. Every overdensity tugged gently, every underdensity let go, and the sum of tugs predicted motion cleanly. Fast forward, structures formed. Gravity, being nonlinear, piled mass where there was already mass. Now neighboring regions talk to each other with feedback. Average over one patch and its boundary shifts because the boundary has its own gravity. You can't just add densities and divide by 2. The middle does something the edges didn't vote for. Meanwhile, the velocity field stops behaving like a polite wind. Shell crossing happens, streams of matter converge, pass through each other, and keep going on different trajectories. Think of cold, dark matter falling into a filament. It overshoots, turns around, overshoots the other way, and layers build up. In configuration space, you see one ridge. In velocity space, you have several coexisting streams. That's a caustic, not a wall, a fold. Stand in the fold, and 2 particles beside you can be rushing in opposite directions, both downhill. This is where effective theories earn their keep. You don't follow every particle. You write equations for large patches, coarse cells whose sizes you can actually measure, and you summarize the subgrid chaos with effective terms. Bias enters. Galaxies don't trace dark matter one-to-one. They're bias tracers that prefer peaks. You account for that with a bias parameter, calibrated on simulations and observations. You allow for stochasticity, randomness born from unresolved physics. The result is an effective field theory of large-scale structure that respects gravity's rules while admitting we can't resolve every fold. Human moment. A researcher stared at a cherished diagram, flow lines sweeping cleanly into a basin, and drew a shaky loop where shell crossing would ruin the picture. "We lied," she said, half to herself. Or rather, we simplified past the truth. Then she redrew the region with bands, not arrows, zones of likely motion with shading for uncertainty. The map looked uglier and felt truer. Meanwhile, biasing complicates the best of intentions. Luminous galaxies cluster more strongly than the mass. Voids traced by bright galaxies can look emptier than the underlying dark matter void. Clusters traced by X-rays can appear heavier during mergers than their actual halos demand. If you mistake the tracer for the truth, you misplace valleys and hills. Reconstruction pipelines try to fix this, iteratively adjusting bias parameters, comparing to simulations, letting Wiener filters pull hard where data are clean and slacken where they're not. But every fix is a choice, and choices leave fingerprints. Here's the intuition that keeps you sane at this boundary. Coarse graining changes the verbs. At small scales, accelerate and orbit make sense. At supercluster scales, converge, diverge, and fold do better. You don't track eigenvectors of every local tidal tensor. You ask whether streamlines as a population are gathering or fanning. You accept that in multi-stream zones, velocity is a distribution, not a single arrow. You plot the mean, the variance, and sometimes the skew, and you remember each tells a different story. Complications are honest. Smoothing too much erases ridges and fakes peace. Smoothing too little hallucinates features. wiggles that look like decisions but are just noise amplified by inversion. Shell crossing wrecks single-valued velocity assumptions. Methods built on linear theory buckle right where the action is. Even the Dipole Repeller label needs care here. Divergence is clear, but pinning a void's exact crest depends on smoothing scales and tracer bias. That's not a flaw. It's a statement about resolution. What nobody knew at the time they named Laniakea was how many neighbors would later be suggested. Larger basins, subbasins, possible superbasins tilting toward Shapley or beyond. Each new layer arrived not as a contradiction, but as a reminder that boundaries breathe with method and depth. A ridge at one scale becomes a saddle at another. A sink spreads into a plain with several low points when you zoom out. The terrain isn't lying. Our lens is. Microstory. A coder swapped kernels in a reconstruction, Gaussian to top hat, same full width at half maximum. The basin edge near the plane shifted by a few megaparsecs, a filament fattened. He winced, checked the residuals against the data and saw almost no change in the fit. So it's the same song, he said, different microphone. The team kept the kernel that made caustics look less like cliffs and more like folds. Impact lands as humility with teeth. The weirdness at the edge isn't magic, it's emergence. The same gravity that drops apples and steers planets also sculpts a web where velocity becomes multivalued, where averages matter more than trajectories, where the map you trust must admit blur. That blur isn't failure. It's the cost of telling a true story at the only resolution our data can support. So are we doomed to drift toward a shore we never reach, or does the river end somewhere else? The folds in the field hint at something downstream we still haven't cleanly resolved. The basin we call home keeps leaning. Past Shapley, the grade may drop again. Our laws still apply. Our language has to stretch. The curiosity gap is real. If not Shapley, then far downstream page. Hypotheses of ultimate sinks. So are we doomed to drift toward a shore we never reach, or does the river end somewhere else? Downstream of Shapley, the map thins. The flow lines don't stop. They fade into distance where our surveys get sparse, our corrections get touchy, and expansion leans hard on every photon. If there's an ultimate sink steering the long slope, it hides beyond the places we've stitched with confidence. That uncertainty isn't a void. It's a field of possibilities, and a reason to keep watching that arrow. Stakes first. If the deepest cause of our lean lies beyond Shapley, then our current reconstructions understate the terrain. That matters for how we apportion pull between local and far structures, for how we interpret bulk flows that span hundreds of millions of light years, and for how we use the cosmic microwave background dipole as a North Star. Overcredit the nearby valley and you miss the distant canyon. Undercredit it and you conjure phantoms. The price of guessing wrong is a skewed atlas that future surveys have to unlearn. Action turns to the limited clues we do have. One line of evidence is structural. Redshift surveys have stitched enormous features like the CFA2 Great Wall, the Sloan Great Wall, and the South Pole Wall. None sits exactly on our downstream arrow, but they prove a point. The cosmic web builds continental-scale ridges and plains. The Shapley Concentration is one such mountain range. There could be others, larger or simply arranged to torque the flow beyond our reach. Some teams have argued on motion grounds that Laniakea may be a subbasin of a still broader domain tilting toward Shapley's side of the sky, hinting at nested hierarchies rather than a terminal bowl. Meanwhile, the microwave background sets hard limits. The primary sky, the temperature pattern frozen when the universe was young, looks remarkably uniform aside from the dipole we read as our motion. That uniformity ties the hands of any theory invoking gargantuan anisotropies just off stage. But there's a subtler tool in that same light. The kinetic Sunyaev-Zeldovich effect, a tiny imprint left when moving clusters scatter microwave photons. Stacked cleverly over many clusters, it whispers about bulk flows on very large scales. Some analyses have teased hints of coherent motion that extend beyond Shapley-like distances, though the error bars are honest and the debate loud. What nobody knew at the time early flow maps crowned the Great Attractor was how persistent the lean would look even after Shapley entered the model. Add Shapley and the fit improves. Add a void behind and it sharpens. Yet residuals remain that point farther, fainter. The far downstream might not be one colossal attractor. It could be cumulative, several heavy domains aligned loosely along our vector, their tugs adding into a long, gentle draw. In a landscape sense, not a single chasm but a terraced descent. Complications keep us cautious. Distance ladders get rickety at the margins where peculiar velocity becomes a small correction to a large redshift. Malmquist bias grows teeth as samples thin. The zone of avoidance cuts the very seam we'd love to trace for continuity beyond Shapley. And bias in tracers, the way luminous galaxies overstate peaks and understate plateaus, can make far features loom or vanish depending on selection. Even the kinetic Sunny Eve, Zeldovich signal is fragile, living near instrument limits and model dependencies for cluster gas. Human moment, a team huddled around a plot that overlaid flow lines on a deep redshift slice. Our filament arced past the Norma hub, brushed Shapley's knots, then at the edge of reliable coverage kept trending southward like a pencil line bleeding off the page. "We're running out of paper," someone said, another voice, "or the story's written on the next sheet." They taped on an extra strip, laughed at the absurdity, and kept sketching arrows into blank. Here's a constraint that steadies the imagination. The large-angle anomalies sometimes debated in the microwave background, the so-called axis of evil, alignments of low multipoles, have tempted some to imagine a universe with preferred directions. But that's speculative territory with fragile statistics and hefty, a posteriori bias. Our safer anchors are the well-measured dipole, the success of lambda-cold dark matter on large scales, and the growing catalog of structures whose some tugs plausibly carve the slope we feel. Any ultimate sink hypothesis has to live inside those boundaries and respect what we already know about Laniakea, Shapley, and the Dipole Repeller. Meanwhile, neutrino masses, dark energy's equation of state, and the possibility of subtle departures from general relativity on vast scales all live in the background as ways the terrain might tilt differently than we assume. Most current data corral those options tightly, but they remind us that ultimate might not be a place. It might be the way the rules weight far hills and near valleys as the universe ages. The far downstream could be a moving target defined by time, not just space. Impact arrives not as revelation but as acceptance. Our map is unfinished by design. We see enough to know the river bends beyond Shapley. We can bracket possibilities, a deeper overdensity farther along, a chain of aligned mass concentrations, or no singular sink at all, just a long slope shaped by many hands. The meaning is that the story dissolves. It's that the last chapter isn't bound in this edition. Microstory. Years from now, a survey with deeper infrared and radio coverage gnaws further into the plane, threads more galaxies across the blind, and extends the arrows by a few precious degrees. The line nudges, not leaps. The river still heads off page. The team smiles anyway. Incremental inches on a map this big feel like grace. So where does the river end? Today's honest answer is that our laws keep holding as the page runs out. The downstream exists as a direction sustained by gravity, clarified by voids, and limited by expansion. The ultimate sink remains an inference past our best horizon, a possibility we can outline, a destination we can face toward, and for now, a name we don't get to write. Human scale, what this motion means here. Bring it back to a room with a humming monitor and stale coffee. An astronomer loads the first sky map where the cosmic microwave background dipole isn't an abstraction but a bruise you can point at. She drags a cursor, measures the hot side, the cold side, and feels that tiny lurch, the Earth, the Sun, the Milky Way, her own chair, sliding through space at 600 kilometers per second. Nothing in the room moves. Everything is moving. And once you feel that, you can't unsee the river. Here's why that lands at human scale. We navigate by assumptions. That up is up, that home is fixed, that maps are places, not currents. Then the dipole says your address is a velocity. The local group feels like a town. Laniakea turns it into a river district. And that river isn't mythology, it's in every calibration you run. Micro story. A grad student takes her first Tully-Fisher dataset and can't make the Hubble relation settle. The slope's fine, the scatter glowers. Her advisor leans over her shoulder and says, "You subtracted the Hubble flow. You didn't subtract us." She adds the local motion vector, watches the plot tighten, and learns the lesson everyone learns once. You can't measure the universe without subtracting yourself from it. Another, a technician re-zeros a spectrograph night after night, chasing drifts that look like instrument mood. Weeks later, the team realizes they'd coded a sign error in the transformation from heliocentric to cosmic microwave background frame. The instant they fix it, the offsets vanish. The relief is physical. The cosmos didn't wobble. They did. That's the viral hook hidden in the math. You have to subtract yourself from the universe to see it clearly. This is where pride and humility swap places. Pride because we can feel the river without touching it, inferring motion from a glow preserved since the universe was young. Humility because the glow tells you your measurements carry a bias unless you correct for the current you swim in. Every redshift you turn into distance. Every supernova you standardize. Every peculiar velocity you trust. All of it leans on the same subtraction. Meanwhile, none of this changes Tuesday. The river doesn't threaten your morning, your family, your street. Andromeda is on approach in a few billion years, not on a calendar anyone needs. The Great Attractor won't drag us into a doom you can watch. Shapley won't either. The push from the Dipole Repeller is a lack of pull, not a shove. But meaning doesn't wait for hazard. It arrives when a map changes what you think you belong to. Identity tilts when you realize you live in motion. Belonging isn't just a cluster membership, it's a trajectory. The Milky Way becomes one of many commuters on a one-way system laid down by dark matter long before the first stars lit. Our future, cosmically speaking, is to watch as the river's far banks fade. The accelerating expansion guarantees that. Future astronomers, if our line lasts that long, will see fewer filaments, dimmer clusters, a sky emptied of context until only our gravitational island remains in view. That prospect isn't bleak if you understand what remains. Local gravity keeps the conversation going. The Milky Way and Andromeda will merge. The remnants will orbit the Virgo cluster's domain as a distant bystander. The river we ride will still be there. It just won't be legible in the sky, which means the knowledge we hold now, a shared arrow, a named watershed, a sense of downstream becomes an heirloom, a message to send forward. Once we could see the banks. Human moment. A late seminar ends, doors open tonight, and a small group stands under the same old stars, swapping stories about first plots and bad subtractions, and that time a flow line on a screen felt like fate. Someone says, "It's strange to feel homesick for a place we'll never reach." Another answers, "Then maybe home is the motion." Heads nod. Silence returns. Practical matters don't vanish in the poetry. Calibrations bake in the river. Surveys report redshifts in the cosmic microwave background frame. Distance ladders quote uncertainties that fold in bulk flows. Peculiar velocity catalogs mark which corrections they used, so others can reweight without double counting. Careers hinge on getting those details honest. A misplaced sign can fabricate a wind. A wrong extinction map can erase a bridge. The river rewards care. And the personal meaning sharpens. Belonging to Laniakea means you share fate with strangers, galaxies you'll never meet that lean the same way. Sharing that fate doesn't make you important, it makes you connected. The thing that looks like deletion from far away, the river thinning into private skies, is also a kind of distillation. What stays bound keeps talking. What drifts away gives you a clearer sense of who you're with. So what does this motion mean here? It means the sky over your house is a snapshot of a journey. It means every measurement you trust has a correction baked in that says, "We're moving." It means our address is a sentence with a verb. And the open question remains on purpose. If the river keeps leaning beyond Shapley, what story will the next map tell? We ride a current shaped by valleys we can't fully see and hills we barely feel, aimed at a horizon that keeps sliding out of reach. If you want to see how cosmic isolation will redraw the future night sky, and what our descendants might still measure, watch the follow-up. Subscribe for more true stories from the edges of reality and the anomalies that bend our map.